Bismillah ar-Rahman ar-Rahim. Today we are going to talk about hydrogen ion homeostasis. Hydrogen ion homeostasis first was meant by acid. An acid is a substance that has certain character like sour taste, or it is substance which dissociates to give hydrogen ion, or it is a substance which has a hydrogen ion donor, or a substance which has a potential electron pair acceptor, or a substance which has donates a cation or accepts an anion or an electron. The end product of the metabolism of all substrates, whether carbohydrate, lipids, and proteins, all of it they contain either carbon dioxide in the form of carbonic acids, and the carbohydrates has the end product is sometimes is lactic acid, which may be in excess, so I'm going to see. Lipids gives keto acids. Proteins get inorganic like sulfuric acid, uric acid, and phosphoric acid. So the end product of the metabolism is an acid, and this acid may be volatile, as I mentioned, like the carbon dioxide. And this carbon dioxide, the daily production is about 13 to 20,000 millimole per day. The non-volatile acids, this is maybe non-organic or inorganic acid like sulfate, urate, nitrates, and these forms about 50 to 100 millimole per day. And the organics, these like the lactic acid, which is produced in about 1,500 millimole per day, and this and keto acids also by about 200 millimole per day, and these are reutilized again with in the normal physiology in the citric acid cycle. Come to these acids which are produced by the cells are usually dealt with what we call buffer, intercellular buffer. We're going to talk about it later, in order to minimize the change in the pH of the cells, and then comes out of the cells. When it comes out of the cells, the volatile acids are excreted by the lung, and the non-volatile acids are excreted by the kidney. When it comes to the kidney, the most important function of the kidney is reabsorption of the filtered bicarbonate and the synthesis of bicarbonate. And this mentions two enzymes, such as carbonic anhydrase and glutaminase enzyme. Carbonic anhydrase may be present on the brush border, like in the proximal convoluted tubules, and within the cell itself. That on the brush borders acts on the sodium bicarbonate, which dissociates into sodium and bicarbonate, and is acted by carbonic anhydrase to produce carbon dioxide, which passes freely to the cell to be acted upon by carbonic anhydrase within the cell to produce also hydrogen ion and bicarbonate. Hydrogen goes out and exchange with the sodium, and sodium combines with bicarbonate to go to the blood. And this carbonic anhydrase is very important, which is affected by the metabolic acidosis, beta acidosis like bacteria of carbon dioxide, angiotensin 2, and hypokalemia. And this topic is very important when we talk about the bicarbonate. So this is the bicarbonate absorption, since 6% in the proximal convoluted tubules, a thick part of the thin globe of Henle and collecting tubules. And then this is the functions of the carbonic acid in the proximal convoluted tubules. Also carbonic acid has a share to get out of to produce hydrogen ion to go out and bicarbonate to go in. And the thick part of the thin globe of Henle, this is bicarbonate, also carbonic anhydrase is very important to produce carbon dioxide to produce bicarbonate and hydrogen ion. Hydrogen ion goes out, but this hydrogen ion has an exchange with disodium hydrogen phosphate to take sodium and leave monosodium hydrogen phosphate, and this is an important point. So the dihydrogen sodium phosphate is a buffer is lost in the form of monosodium hydrogen phosphate, and one atom of sodium is absorbed with bicarbonate. So we restore the sodium bicarbonate in this process. Also, the same thing for the collecting tubules, but the exchange here is the carbonic anhydrase here produce hydrogen ion, which is excreted by its pump or in exchange with potassium. The second part, which is ammonia, the ammonia, this is the second enzyme, which is a glutaminase enzyme, which act on glutamine. This is in the kidney to produce ammonia and glutamic acid. and acts again these glutaminyl on the glutamic acid to produce alpha ketoglutamate acids and ammonia. So the end product of the metabolism of this glutamine by glutaminase in the kidney is the production of ammonia, which is there, and the neutralization or decrease in the acidosis of the urine itself in a process to help the excretions of hydrogen ion, at the same time absorptions of two molecules of bicarbonate. And this is essentially, this is a glutamic acid acted by glutaminase to produce ammonia, and another glutamic acid to produce ammonia, and then alpha ketoglutarate acid in the citric acid cycle to produce two bicarbonate molecules. So the end products of the metabolism of the glutamine is the productions of bicarbonate, which is absorbed to the tissue, to the blood, and the productions of ammonia, which enters into the medullary interstitial tissues, and then is retained within the medullary interstitial tissue till the function comes. Imagine that the end product of the metabolism of the protein, like sulfate, phosphate, something like that, when it reacts with the powerful sodium bicarbonate, it gives sodium sulfate, sodium phosphate, sodium urate, and then carbon dioxide and water. These will be filtered and come to the distal convoluted tubules, and in distal convoluted tubules, the carbonic anhydrase will act to produce hydrogen ion, and this hydrogen goes out to make some sort of exchange with this to absorb sodium, and this sodium which is absorbed by this pump. So the hydrogen ion will go out, sodium is absorbed from the sodium sulfate to give sulfuric acid, and this is sodium will go with bicarbonate, and so we synthesize and replace the bicarbonate molecule again. But in this case, sodium sulfate has been changed into sulfuric acid. And this is very important part. The sulfuric acid here is the pH of the pH here. The pH will be a little bit low, and when it comes lower than 4.5, when the pH comes lower than 4.5, this is a problem. A problem for what? Again, a problem for this pump to act. This pump to act, there should be some sort of concentration gradient. The hydrogen ion here should be less than that in order to make it easy for the hydrogen ion to go out to the urine. But if there's some sort of acidosis, the pH is low, this means the hydrogen is high, and this is difficult. So comes the rule of the ammonia to come to combine with this hydrogen ion to make ammonium, and in this case, the NH3 will combine with hydrogen ion and of this sulfate of this sulfuric acid to form ammonium sulfate, ammonium phosphate, ammonium urate. And in this case, the pH will go again, and instead of being lower than 4.5 to go above 4.5, and this make it easy for the hydrogen ion for this pump to act and to restore the to excrete hydrogen ion and restore the bicarbonate again. So the problem of acidosis is the balance between two things, productions and excretions. This may be some sort of overproduction of the acid, like lactic acid. Lactic acidosis in case of hypoxia or shock, it will be more than the capacity of the liver to clear. Liver can clear about 3,500 per day. This increase in lactic acid will lead to some sort of increase in the hydrogen ion, and this is acidosis. Or the ketoacids, and in cases of ketoacidosis, where there's some sort of deficiency of insulin and the lipolysis increase, free fatty acid increase, and this free fatty acid goes to the beta oxidation with the excessive productions of keto acids, beta hydroxybutyric acid, and acetoacetic acid. This is a very important point. This is overproduction of the acid might lead to some sort of increase in the acid in the blood, and this is acidosis. Or decrease or the renal impairment, decrease secretions or decrease excretions of this acid, like inorganic acids. In this case, will accumulate and exhaust the buffer, and the hydrogen ion will increase. And the last thing is loss of the buffer in the case of renal tubular acidosis. The second part, which is the volatile acid, which is carbon dioxide. Carbon dioxide, as we see, this is a daily the production of carbon dioxide is about 240 ml per minute, about 360 liter per day, and this forms about 13 to 20 thousand mole millimole of per day. So this is a large volume of carbon dioxide is produced. About 70% of it is acted on by carbonic anhydrase to produce bicarbonate, and this is very important. And so the bicarbonate, by these actions, about the bicarbonate in the venous side will be 1.5 milliequivalent per liter higher than that of the arterial, and about 20% combined with the globin to give carboxyhemoglobin, and the 7% only, and these physiologically dissolve, and these are responsible for the increase in the partial pressure of carbon dioxide in the venous side by about 6 millimeter mercury. So when we come to this at the tissue sites, these some sort of handling of the carbon dioxide, and the main important functions in the RBCs. This is RBCs is very important for these functions, which contains the carbonic anhydrase. So on the venous side, the pH is less than that of the arterial by 0.05. Bicarbonate is larger than the arterial by 1.5. Carbon dioxide is larger than the arterial uh, uh, by about uh, by about 6 millimeter mercury. On the arterial zone, when you come to the lung, the reverse happens. By the partial pressure of oxygen is high, it goes displaces the hydrogen ion, and this hydrogen will combine with the bicarbonate in the reverse chloride shift to with the action of carbonic anhydrase to make the carbon dioxide go out through the lung and to get rid out of carbon dioxide. So the carbon dioxide, the determinations of the carbon dioxide depends on two things, on the productions from the tissues and the excretion by the lung. In this formula, carbon dioxide output multiplied by the barometric pressures divided by the tidal volume minus the dead space and the respiratory rate. So the carbon dioxide can increase with excessive productions of carbon dioxide, then hypermetabolic state maybe, or the decrease in the tidal volume due to pneumonia, aspirations, heart failure, or pneumothorax, or in COPD due to the spasm, or dead space like that in the case of pulmonary embolization, or decrease in the respiratory rate by any cause. To conclude that this is the acidosis may be respiratory, increasing the partial pressure of carbon dioxide due to hyperventilation, or it may be secondary due to metabolic alkalosis, or the acidosis may be metabolic. This is primary, as I have mentioned before, decrease in the bicarbonate, or due to neutralization or due to loss of the bicarbonate, in addition to decrease strong and difference. We're going to talk about it, decrease in the buffer base, increase or normal strong and gap, secondly due to respiratory alkalosis. Alkalosis, this means the decrease in the acid itself and increase in the OH. This is maybe respiratory due to decrease in the carbon dioxide, primarily due to hyperventilation, or secondly due to metabolic acidosis. Metabolic alkalosis may be primary due to increase in bicarbonate. This may be associated with increase in strong ion difference, increase in the buffer base, or normal strong ion gap, but may be secondary due to respiratory acidosis. And thank you.